Kinetics Notes, Example 16. A certain reaction is second order. It takes 45.2 hours for the concentrated reaction to go from 0.4586 molarity to 0.1525 molarity. What is the rate constant? So we first can establish that it's second order. We know that this is our time, right there. This is our initial concentration. This is our final concentration. It wants to know rate constant. That means we're solving for K. Because we know it's second order, we've got to use something along this row right here. And we need to find rate constant, so we need to have K. We don't have a rate, so this is not going to help us. We don't have a graph to make a slope from, so that's not going to help us. So the only thing we can use is the integrated rate law to solve for K. So from that diagram here, you're going to see we're going to put 1 over final concentration minus 1 over initial concentration equals K times T. That's what I've done here. As I have mentioned before, it is highly recommended that you put these in your notes like this, that you have these, you put the basic formula, generic formula, that is required for homework. I highly recommend you do it right above any work you're doing. It is required for homework, so make sure you're putting this generic formula, the basic formula you're going to use. Alright, so then we know 1 over 0.1525 molar minus 1 over 0.486. Remember, this is your final concentration, says to put it here. Initial concentration formula says it to put it there. K times T, we're going to take 1 divided by this and we get this. When we take 1 divided by 0.4586, we get this. We still set it equal to that. When we subtract these two, we get 4.376 equals K times time. And then we're going to divide both sides by 4512, and this should still say hours here, to calculate the value of K. So there our value of K is for this problem. Again, make sure you have shown your generic formula on every single calculation. Before you start any calculation for any homework or notes, you should always be putting the generic formula right before you do your work, or right above your work. Part B says, what is the half-life of the reaction when the reactant is this much? Okay, so we're looking for half-life. We know the beginning reaction, the beginning concentration, or the now concentration is this, based on this problem. If we went back and looked at our diagram here, half-life for second order is 1 over K times the initial concentration. This is the half-life column, remember? So 1 over K times initial concentration equals half-life. So we have half-life equals 1 over K times initial concentration. We're going to put 1 over K, which we had from previous work, part A. This is the concentration of the now. When we do this math, we get 179 hours for the half-life. Okay, so C is how long will it take to rearrange 31.47% of 0.61485 molar solution. Our K is coming over from the other side. I'm going to go grab the units. I'll be right back. There, I put the units in there. So this K came from part A. As we read this, we know we're looking for how long. That's a time. It says rearrange a percentage, and then we know that of this much. This is our starting amount, our A naught, our initial or beginning concentration. When you're given a percent, you must decide if the percent represents either percent remains or percent used. When you're given a percent, it will represent one of the two. You just have to figure out what verbiage and what it means. I'll help you with that next. So if I rearrange it, that means I'm using it, right? If a reaction rearranges its reactants, it's using up its reactions. So when you think of rearrange, you need to think of used. So in your homework, in your practice, when you see the term rearrange, you will know it means that you've used it because you've rearranged those reactants and they've been used up. So we're rearranging 3147. In other words, we're reacting, same thing, 31.47%. So here then we know that percent remains is A over A naught. We have to subtract from 100 because we don't have remains, we have used. So we take 100 minus 3147, we get 68.53%. And then remember, percent remains equals A over A naught. A over A naught equals 0.6853. 0.6853. What we have is our A naught, so we can plug that in this appropriate space, and then we can cross multiply. So we can put this over 1, 0.6853 over 1, and then cross multiply. And when you do that, you get 0.4211 molar for our concentration here for A. So now we have A and A naught because of the relationship between percent remains equals A over A naught. A over A naught, pardon me. So we can plug in our value. We know our A is 0.4211. Remember that was from this work right here. And we know our A naught, So again, look what I did. I put my formula in here as I requested and expect that you have the generic formula up above where your work is. And then we're going to put in the A naught here. This is the K that we had from previous work times time. Remember, we were solving for time. When I take 1 over this and 1 over this, I get these two values. And then when I subtract them, I get this value. I'm going to divide both sides by 9.68 times 10 to the negative 2 to solve for time to get 7.73 hours. As always, I recommend that you pause the video and go through this calculation so you know what to do on your calculator when you have to do one in practice. Part D says, how fast is a 0.6257 molar solution being changed to a specific product? So how fast is this much? How fast does not measure time. How fast measures rate. That is a very important thing not to miss. How fast is not, how long is time, how fast is rate. So we know this was second order based on the previous prompt. So we know we're going to rate equals K times our concentration squared. So we're going to take rate equals K. We know the K from part A. We know the concentration from the problem itself. We're going to square that. Make sure you square both the units and the numbers. And when you get that, you get this answer, which is 3.79 times 10 to the negative second moles over liter hours as your rate. Again, as always, you should have the generic formula up above, substitute items in with units, and then use your calculator to make sure you can get my numbers. All right, for 16E then, it says, how long will it take 17.58% of a 0.2175 molar solution to remain as a reactant? So remember, anytime we have a percent, first of all, we know that it is from the previous work. We knew that it, oops, I don't have to go that far. We know it's second order, so we're following this scheme right here, this row of formulas. We're looking for time. How long is time? So we're going to use the integrated rate law, okay? And we have a percent. So anytime we have a percent, we always want to consider what the percent represents. In this problem, as you read through this, the percent represents amount remains. So no need to subtract from 100 because we know it's remains. We would not subtract from 100 because we already have remains. Percent remains equals A over A naught. A over A naught equals 0.1758. Remember to write your percent as a decimal. Remember, we did not subtract from 100 because the percent already represented percent remains. Then we're going to put our initial concentration in for A naught, put this over 1 and cross multiply, and get 0.03824 for my A concentration. Then we go back to our generic formula. Remember, it's required that you show the generic formula. This will help you stay organized and get correct answers. I'm going to plug 1 over A, which we calculated by our percent remains work over here, by our side work. So we put 0.03824 here. And then our A naught, 1 over A naught was what we were given, 0.2175. We already knew K from previous work, part A or B, whatever that was, previous work. When I do the 1 divided by this and 1 divided by this, I get these two values. I subtract them, I get 21.55. Set that equal to K times T. Divide both sides by K, and I get 22.62, or round it to, this was incorrect before, I'm making correction here, this is 23. So T equals 223 hours.